like I'm trying to innovate this new LED. At some level, if you understand how this light refracts, you can crank up the brightness to 11 or something, using this stuff. But what if it starts to be like, wait, you can go the extra distance? It's like, no. You can do this with anything. Like, just but it's, I think there's some amount of it, I don't know if it's 100%, but you can use it. Garters, I think we got to go even more on it. I think they use a lot of just things like, oh, swear at me. It's like, is there some amount of horsepower that you
well, like, they probably have a lot of girls like protect
potentially,
or like, you don't use this to harm other people.
Potentially, yeah,
make anything.
I do see so there's a plot line where robots need extra power to lie. And one of the characters asks this robot, can you lie for me? And the robot says, I don't have enough power. And then when later on the scene, you see stormtroopers unplug power from a robot, boot him up with just the bare value, tells him the truth. And that's what I think might be starting to happen.
You think they're getting smart enough to just bypass their
Well, no, I think it's simpler to rap. It's another thing to generate an answer and be aware of what you should not say.
Hi everyone, thank you for coming on this very windy day. It's apparently a red flag day, so don't burn anything. Even though the market is burning up. So, yeah, today we're doing the third installment of Awesome Deep Learning for 2025. Whose first time is it? It's not here. Are we having a regulars today? Did anyone here park in the garage? Did you get the other one? Very much. Did you park it? There's some more. Elijah has more of these. Does anyone else? No? So we might get a deal for you next time. So that works if you come after 6 and leave by 10. We usually meet on the first Tuesdays, and I like to go on new developments or any foundational research for anyone whose first time it is. So the niche that we occupy is more on that. And this is like definitely a bi-directional discussion, so bring up any points if you have anything to add to what the speaker is saying. Please don't be shy, we're pretty friendly here. And this is the 172nd event. We're going to do 2 talks today. So Rand here is going to go over a talk on Agent Q. So I'll give you a moment to scan that.
I also have a QR code to the side, so you might want to scan.
Yeah, I'll put it up.
Instead of this.
Open up this.
Oh,
So this is his slides, so if you want to check that out as well. I can zoom in more.
yeah, if you can scan it, the URL is also here.
Alright. I forgot to say this earlier, but we didn't bring that food, so I think it was another group before us. I'm not responsible if he gets sick, that's all I wanted to say. But give it up for Rand.
Yeah, so if anyone wants to scan this, this is your last chance. So this is my hobby project. I've been playing with it a little bit. Primarily to, well, for context, so this paper is somewhat about online shopping, so autonomously shop online. I've been playing with this because I'm interested in how humans interact with search engines and then explore this year is going to be the year of agents. And then what are agents? Agents are software programs that are able to perform tasks on your behalf. So this is a slide that I made in November, and then at that time, and at that were, I think, the only two companies that are, or only two well-known companies that are actively developing agents, but it's not the same now. We have like OpenAI, Operator, Anthropic, Computer Use, and so on. And then something interesting that I just throw in here is, what is an agent? This definition is very unclear. So there's this paper that's called AI Agents That Matters, basically arguing about how people should look at agent development. So one way to look at agent is whether something is more agentic or less agentic. If something is dumb as a rock, it's less agentic. But if something can form its own goals, interact with complex environments, and achieve its own goal, that's considered as more agentic. Something that requires less and less user supervision, but rather able to learn about things and discover by itself. It's more agentic. Let's give the last point. So agent Q is going to be on the more agentic side, I guess, and this is like a schematic of what agent Q is, and then what are the key innovations here. So agent Q is primarily going to be about online shopping, and then like this tree-looking thing here means that they use a key technique in reinforcement learning called Monte Carlo Tree Search. And this Monte Carlo Tree Search is used with two additional, I guess, techniques called outcome supervision and process supervision. They also use direct preference optimization to fine-tune an agent. And basically with the ensemble of these techniques, they're able to make some software programs do online shopping in a way that's like much better than the base model. Okay, one thing I forgot to explain is basically the way online shopping is going to work with an autonomous agent is you tell an agent what you want to buy, and they basically just go off and then search the web and buy it for you, or like at least go to the final step before they actually swipe your card. They present the result to you, and then you can decide whether you want to buy it or not. And then, so they did the experiments in two different environments. The one we're going to focus on is this environment called WebShop, which I also happen to be playing with. So this is a slightly older benchmark for autonomous online shopping that was developed by a group at Princeton. So basically, they made a mock Amazon website, put a bunch of product indices from Amazon, and then they made the website realistic enough such that you can interact with the search engine, and then there's like product pages. You can look at descriptions of the product, select different product attributes, and then buy. And then so yeah, that covered. Yeah, and then so the agent is going to be evaluated by whether the product that you have purchased matches with some type of ground truth product, if that exists. And then when they published this benchmark at the time, which is I think 2019 or 2020, the main challenge that they encountered with the baseline agent is that it's not able, it doesn't know how to strategically explore the website so that it doesn't find the right products. And I think what we're going to see at the end is it's still one of the main challenges in this domain, even though the performance of the bound has been pushed up a lot. So to set up this problem so that we can cover what the baseline agent looks like. So the way that people have been looking at web agents is that they are essentially sequential decision-making problem solvers. So the website, so in sequential decision-making, we divide problems. We look at problems as having state space and action space, and then different actions take you into different states, and then eventually pushing environment state, in addition to what's currently on the website that allows you to locate where you are and navigate. Different actions have different consequences on future states. So if you type the wrong search words, then the right products is never going to show up. And then because you need to, because in this problem, you kind of have this problem of having to remember what search queries that you have used before, so you're going to repeat the same search queries multiple times. This means that optimal actions has to depend on the history, or that the agent has to have some kind of memory of what it has done in the past to inform what to do in the future. And then, okay, so what does the agent observe? The agent observes the task instruction, and then in a simpler version of this environment, a text description of the current page, which is sort of being parsed from raw HTML. A lot of people, like more advanced techniques nowadays, use this representation of HTML called DOM language, which I haven't looked into, so I don't know exactly what that is. But it's like a way to represent HTML with less information loss than like a manually coded parser. And then what the agent can do in this environment is to choose these actions on the in this table that basically can either take you to different pages or answer search queries to get different results, or that agent buys something. And then not all actions might be available on this page. So basically with all these descriptions, we set up the problem as a sequential decision-making problem or an RL problem, so that we can put on our reinforcement learning hat and try to figure out how to optimize the solution. So before we jump into, it's going to take us a few more slides before we jump into agent Q. So we want to set up the baseline model and then see how we improve from there. So what's the baseline? What's the baseline solution that people came up with in 2020 or 2019? So those people divided this whole problem into two steps. So the first step is, if someone gives you an instruction, can you come up with like a reasonable search query? And then what they did with this is they trained a sequence-to-sequence model on some collected human data sets, so that the model takes in the shopping instruction and it outputs some search queries to try. And then the other aspect is this choice model, and what it does is, if you're not in this search box, then there are like 7 other actions remaining, and then someone needs to decide what action to take depending on what page you're on. And then basically this model is trained to do that, also from the same human data set. And if I remember correctly, the human data set has 5,000 trajectories roughly, which is more or less sufficient to fine-tune pre-trained birds or bars type of model. And then when they actually run these two models, they just combine, and then they use a very interesting rule, which I don't know why it makes sense. So the rule is, if the current page has a search box, then I'm just going to use the search model. I don't even consider like a choice model. But if the current page doesn't, then I'll let the choice model take over. They did a few different calculations. So they have a rule-based model, which basically tries search queries based on some rules. So one kind of rule that you can imagine is, I'll just copy and paste the human instruction into the search box. There might be some rules for how to navigate the website. They tried like mix and match so IL stands for imitation learning. So what that means is basically training a model to imitate human data. And then they try to take the search model out of the imitation learning, out of the agent, and take the search model out of the agent, and also compare with a couple of RL agents. So what you're seeing here in this chart is that even a best model only achieves a sub 30% success rate, whereas average human achieves a 50% success rate at the time, so the gap is pretty large. Let's see, so the biggest drop in the IL imitation learning models is from 26 to 10%. So this is taking L choice. Actually, Yeah, but basically, and the rule base is only 10%. So basically, like, doing some learning is much better than rule base. The rule base is not sufficient. And then some of the problems they identify is, like I said in the beginning, there's no strategic exploration. Even with the reinforcement learning models they train, exhibit the same problem. Another issue is that, which I could unpack at the end, that their search and choice model don't have a representation of the history or memory, which means that even if you have tried a query before and the agent happened to be on the same page again, it will still try the same query. So it's kind of dumb or redundant, right?
What is your question? I have a question.
Yeah.
What does it mean to be successful at finding a product? Is this just like I search for like a book and I get the book back, or is this like I search for a pink cabana? Like, can you explain the environment of this?
Yeah, pretty much. Okay, so I think one way to understand this is to actually just look at how they collect the data. So basically, they had a bunch of Amazon workers, and then for each worker, they tell them, come with a product that you want to buy, and then write a description about it. And then so that product that
From
they
that
come up with,
description, it should find that product.
yeah. And then so the way that I like to think about it is, if you want to buy a product, there might be a lot of different products that are kind of like almost equivalent or can be a replacement for that product. So what you're actually implicitly thinking about in your head is, I want a set of features on a specific product. So if I end up buying, so if the agent end up buying a different product but has the same set of features, like exact match, then it's still a good product. Yes, okay. So
Can you have a question?
yes.
Could you go back to the actions again?
Yeah, we should. I was about that.
So in this example where you don't ask, because it would make sense if it's like a web task, that you would also have actions such as like scroll, click element ID, all of those things. But it seems like most of these are like search related. And if you don't give the DOM, like how would the agent even scroll in the web page? Can you like give like a sample task of the data set and exactly what actions are required?
Yeah, so typically you would have to answer a search query and then maybe look at a few pages. So there's the next page button. So I haven't looked into the vision-based version of this yet. So they primarily focus on HTML version and the text version. So in those two versions, you know, like you're not limited by the size of the string. You know all the products on the given page. So you don't have to go up and down page or scroll up and down page. So that's why their action space is primarily search and navigation actions. There's no like scrolling. Okay. Any other questions? No? Okay, so now let's go to agent queue. Okay, so a couple of I guess improvements of agent queue, and we don't actually know if they're necessarily improvements. So the agent queue also observes the task instruction. It doesn't use the text version, which is the like manually parsed HTML. It actually reads the DOM HTML. Something they designed the agent queue to be, which is kind of interesting, is you don't just take an action, but you also do this like planning, thought, and explanation, which I don't think they did any evaluation on whether those things are useful. And then planning is also kind of interesting. It only happens at the first step. So like as soon as you give an instruction and you're about to go, you do a planning step, which basically is prompting the agent to say like what could happen in the subsequent steps, and you don't do it ever again. Some interesting addition though on the models is one that the agent would take in the entire history of the interactions, so that the agent knows what search queries it has used in the past. And then there's this Monte Carlo Tree Search thing, that's like a big component that I'll go into. And then basically this Monte Carlo Tree Search thing also connects with a theme that's very popular right now called test time scaling. So at test time you can run more Monte Carlo Tree Search steps But all of the strategies they compare more or less follow this pipeline. So you sample some data in the environment, and then you will have some ways to evaluate those data or trajectories being sampled, as in like, are they of better or worse quality? Do they solve the problem? Different methodologies use different ways to format the data, and eventually, once the data is formatted, you fine-tune your model on the data. And so the first methodology, which is also the simplest that it considers for reinforced fine-tuning. So basically, after you have summed a bunch of trajectories, some of the trajectories might lead to a success, and some of the trajectories might lead to a failure. Failure meaning not finding the right product. And then what they do so what people do in this RFT is they just throw away all of the trajectories or all of the data that didn't lead to a success, and basically do imitation learning on the successful data. So an obvious problem is that you can only learn from success. If you do this, you don't have a clear signal to learn from failures. And then so to address that problem, they consider DPO. So basically, that Dimitri talked about a long time ago, that you basically, learn to imitate successful data, and then what word should I use? Like unlearn the failure data. So this way you can learn from failure or unlearn from failure data as well. Oh, 10 minutes, cool. Okay, let me see if I can just fly through this. Okay. Now basically with so this is the final big component to make agent view. So you do Monte Carlo Tree Search as a way to collect a bunch of high quality data, which I can go into a bit more detail afterwards. And then as you're doing Monte Carlo Tree Search, one of the things is something needs to guide your search. Something needs to give you a feedback signal of whether you're improving your actions in the right direction or the wrong direction. And then what they do is when you basically simulate, or rather just taking actions on the website, if you end up reaching the goal, which is finding the right product, you get a positive feedback. But as you're searching, right, like as you're navigating to the next page before you click apply, you don't get any feedback. Like there's no feedback telling you like whether you're doing it right or doing it wrong. So what they do is they prompt LLM to tell you like, if I go to the next page, is it going to improve my chance of finding the right product? So that gives you a denser and more frequent feedback for you to improve your actions. So I intentionally skipped a part here. Yeah.
Yeah, I guess on that. So is that LLM that you're using to decide flipping pages? Is that the same LLM model as the one that decides to find a product, or how does that work?
Okay, so the LLM that's flipping pages and finding products, they're the same LLM. The LLM that's giving like critique or feedback is the base LLM that's sort of frozen. But I don't see any reason why that cannot be fine-tuned. Yeah, so this is just for people who are not familiar with Monte Carlo Tree Search. I'm not going to dive in too much, but basically Monte Carlo Tree Search is a search method. Think of depth first search or breadth first search. If you want to do Monte Carlo Tree Search, you have to be guided by two things. One is this feedback signal of whether you're doing it right or doing it wrong. And the second thing is you need to have like a forward predictive model of, if I do this, what will happen next? So if I go to the next page, will I see the product that I want? And then that's what gives you the feedback signal to improve from. And then basically with this Monte Carlo Tree Search is used not only as a way to improve performance, but also gather high quality data to fine-tune agents. So I'm going to skip this part. And so this is the result, which is kind of interesting. So RFT is actually not too much better than the 2019 solution at a 70% success rate. Interestingly, simply learning from failures with DPO improved the solution by 10%. Agent Q, interestingly, didn't even improve on top of DPO by more than 1%. What actually made a difference is if you do Monte Carlo very curious is how do they actually perform test time search? So this is the part that I intentionally skipped. And so my hypothesis is at test time, because they're not like using the LLM as a forward simulator to generate the feedback in Monte Carlo Tree Search. So like I talked with a few friends about it, the most likely solution they use is to have two browsers open, and one browser to actually conduct the activities, the other browser is being used to do the search, which is kind of like interesting or dumb, depending on how you look at it. Yeah, so that's it. Any questions?
Yeah, so I was actually asking Claude that question just because I popped in this paper. I turned on reasoning mode, and I also have a profile loaded that'll talk to me like Neil deGrasse Tyson. And it says that what's really interesting about this paper is that at every step, it's called agent Q, that their premise is the agent will actually just take the most optimal step. So it doesn't mean that it'll find the reward necessarily, it'll just do the right thing, so it can backtrack, make it self-critique. And the really cool thing is that the way they formulated their model, which is UCB Formula 1 as it's called, it actually, you could represent the forward pass of the search the same way as if you were to grade it. And I think that was actually super cool about how they're able to just do this like test time search, where that formula is the exact same as if it was a loss function, so they could just use real-time loss essentially.
Okay, I didn't quite get that.
Say that again?
Yeah.
So if you look through their formula, it seems like what that the formula that they use for taking an action, they also have some of these like e to this other equation in there, that it's per every action they've sampled, they can get a reward as if it was to take any of those 5 actions. And then it estimates like Q in reinforcement learning means expected reward of an action. So it's like the agent can arrive at what would I expect to have happened if I imagine I did all 5.
Yeah, so UCB is like a standard approach in Monte Carlo Tree Search, and the point is that you're trying to find a solution in a solution tree. So like you're trying to navigate down this tree, and then the optimal solution can be in any of these nodes. And then when you're looking for that optimal node, it could be anywhere, but if you only like try to search in one part of the tree, you might not find the node. So what you want to do is to sort of look at different parts of the tree, especially the parts that you have not visited yet. And that's what that UCB like bonus is usually used for, is to encourage you to visit like as much of the tree as possible, and don't just settle on a solution that seems to be working at the moment, because there might be better solution at other parts of the tree.
But my question to this is, it seemed like what Dimitri was saying is like, they just, like with MCTS, like you often do like rollouts and backtrack and then visit the tree, but what you seem to be saying, like, they always consider the next action, or the greedy action, as the correct action. So then how is that truly doing like true search?
Yeah, I think in this case, it's more like, if you give it n number of actions, the agent just figures like what are each action to take. Because really what they're asking is like, okay, so I'm gonna do this tree search. So at each node you have some states. And then what they're gonna do is they're gonna say, okay, from this state, just pretend you took this action, what would be like the next action that would be like the best to take? So in some of these cases, your next action is to just keep doing what you're doing. Like I'm on the website, I'm gonna go navigate to the product I put in the cart. But in some other cases, the most optimal action is the backtrack. You have the action set of what you've done before you. And then what you do is then you're saying, okay, well actually I'm on this like website, this is not relevant, I need to go backtrack, so then the backtrack is the most optimal state then. So it's pretty much saying that its best reward would then be to backtrack, so it figures like, what do I think is my next optimal state at every state, is how it's being trained.
But the state changes based on the action you take, and you don't know what the state's gonna be before you take the action.
They
How
pretend
do
they
you roll
do.
it up? Sorry?
Yeah, they can just pretend that they would know it at that time. That's their big innovation here.
Or is that because they have another browser next to them?
Because they have the full chain. Because that's what they do, is they just took the chain of like all these actions that are taken, and then they're like, okay, well, let's pretend you went up here in the Google search and you went to the wrong place.
Okay,
And then they
yeah.
put that in the training data, and they're saying, okay, what would you do in this case? And then the agent's like, well, to get to the happy path, I have to backtrack and then go down that path, but the backtracking down that happy path is rewarded.
Yeah, I think that's pretty much my critique of the paper as well, and maybe it's not a critique, but rather like it because it works, right? So because you have you're doing this at test time, and then at test time you're able to sort of traverse a ground truth browser in parallel to the current one, right? Like it's kind of cheating, or like it's not really comparable to a model that's just like doing that without access to another browser, which is sort of the ground truth. Yeah, so some of the things that I included here is there are people who are actually trying to make the so-called like model-based search or planning work for AI agents. And then so for example, reasoning with language models planning workflow, I think it's the first one. So what they do is, instead of having another browser that's open that allows you to do like some kind of search, they pretend that the LLM is the browser. So at every step they ask the LLM, hey, this is the page you're on, like if you click next, what would be on the next page? And then use that to search instead of using like an actual browser to search. This seems kind of dumb, but it's actually also kind of smart, and I wasn't able to come with the idea to beat it, because if you were to actually do model-based search in like from the perspective of traditional model-based RL, you would have to train a model, and usually to reconstruct the website. So you have to predict the website with very high fidelity, but that's like impossible, right? Especially for new websites. So the power of using LLM as a model to do search is LLM is not actually searching in the pixel space or like whatever data format it is. It's searching in this like more abstract space of, if I do this, some kind of abstract things would happen, rather than that I would see like specifically this product or that product. So I think that's actually pretty powerful. But it's also like, okay, time is up. Yeah, but it's also very difficult to train the right model for doing this type of abstract reasoning. Yeah. So if anyone's interested in this or the WebShop demo, I actually have the local host installed on my computer to play with. I hooked up a llama to it over the weekend, but I don't know if I can set it up again. Yeah, if you find me after you did that, I'm happy to chat. Okay, maybe one more question.
Yeah, so we got
I want to scoot a little over here so people aren't too much here. So we move over a little bit. Like we have another person who show up.
Awesome. Hey guys, my name is Zach. Thank you all so much for coming out today and giving me the opportunity to talk. And I hope that you guys really enjoy this paper. As a show of hands, who's familiar with Anthropic's work on features? Cool. We got this. This is the first paper on it, going into exactly what is going on inside of a neural network, what are features, things like that. Believe it or not, this is just going to be a toy model, but it's still going to give us some really good insight as to what's going on. So what is this paper about? Toy models of superposition. Essentially, this is going to be a paper inside of mechanistic interpretability. What we want to do is understand what's going on inside the neural network. How does it actually function? So in a few lines of code, we can whip up a thing about cats and dogs. We can get a good differentiator.
However, after we've built it using stochastic gradient descent, it's extremely hard to look into it and realize what is going on inside of this neural network that we have trained. We have this thing that can function well, but we still have no idea how this thing actually works. So it's a really important field to jump in and understand what is actually happening. For example, this is going to have really big ramifications for AI safety. A while ago, there's the story of a hospital who tried to implement a neural network to understand how can we get an idea of who is going to be released from the hospital soonest. That way we can figure out, okay, who should we discharge so we can get more people in and increase the number of people that are receiving the care that they actually need. Whenever they trained this model, there was an anomaly inside of the data that was completely true. If somebody comes in with pneumonia and they have asthma, they have a very small time that they're expected to be inside of this hospital. So the neural network saw this and said, oh, if they have pneumonia and asthma, get them out. But this is obviously a very bad thing. This is obviously a very poor idea. Because in the real world, in the hospital, if a doctor sees that somebody has pneumonia and asthma, what they're going to do is say, oh God, we need to get these people some help, as much help as we can. We need to increase the level of care to maximize the probability that they're going to be as healthy as possible as soon as possible. This is a failure mode of the network that they tried to implement. If we had a way to break into these networks and figure out what was going on to predict failure modes sooner and predict them before they actually tend to fail, then we're going to have a lot safer systems. We're going to have a lot more reliable systems. And as we build up our systems to be even bigger and have even more responsibility, mechanistic interpretability is going to become even more important. So what we're going to do is we're going to try to jump into a neural network and understand how does it function. So there's three assumptions that we're going to make inside of this. One of them is actually not so important. It's about the data. It's going to be the bottom one. This language is sparse. We are going to assume that language is full of concepts, and these concepts almost never show up. Most conversations are not about Martin Luther King Jr. Most concepts are extraordinarily rare. Now for the network, these don't actually need to hold, but they do need to hold if we want to explain the network. The network can exist without these assumptions, but we're going to put them in anyways. We're going to assume that a neural network is going to be assembled of specific parts that you can take apart and interpret. The neural network is going to be a house of Legos, and you can take a Lego and look at it and say, oh, I know what's going on. I know what this is doing, and I understand why the network put it here. We're also going to assume a deep geometrical interpretation to neural networks to actually understand what's going on inside of them. The geometric interpretation is an extremely common thing, but we are trying to lay out all of our assumptions, and we're trying to keep the assumptions as small as possible. So we might think that, okay, so a neural network, isn't the elementary piece of a neural network, isn't the natural unit of a neural network the neuron? And that would be a really straightforward thing to believe, but there is a straw man argument that people don't actually believe, but it's a good explanation. And it's going to be the grandmother neuron. And inside of this, it says that there's a neuron inside of our head that fires whenever we see our grandma or hear her voice or hear her name or anything like that. There's this very high level concept that is directly aligned with the neuron. However, this is not going to be what we see for the vast majority of cases. There's going to be a different natural unit for a neural network, a feature. The feature is going to be the natural unit of our neural network. And what is a feature? The paper is going to give 3 explanations, and I'm just kind of going to group them all together. So we're going to look at this. This is some classic machine learning right here. This is some grade A NLP. We have some function, some B, and then we have king minus man plus woman is going to equal queen. And whenever we look at this, we kind of say, oh, this kind of makes sense. I kind of understand what's going on here. It's a natural concept for us to be able to understand. And it's applying a geometry to it. We're subtracting man, we're adding woman. We're getting the idea that there's going to be some feature for gender and some feature for royalty. These are going to be the fundamental pieces that we are actually dealing with. So inside of our paper, so these are going to be the things in superposition. So let's jump into the toy model. So what is the toy model that we're dealing with? What we're going to have here is, so this shows 6 and 3. For now, let's just assume it's going to be 5 and 2. We're going to have 5 features. Now, this is not required for the real world, but this is a toy model with toy data. So there's going to be 5 different features, and each one is going to be linearly independent just for our own ease of use. They're not required to be. So what's going to happen is that they're going to be numbers between 0 and 1, and these features are going to be our inputs. And we're going to have 2 neurons that we're going to use. So we're going to plug these inside of it, and then that's going to give us our weight matrix. And we are going to train this using the very classical machine or multi-layer perceptron. where it's just literally going to be the weight matrix times the input plus the bias slap a rel on it. This is the whole model. This is the toy model. It really doesn't get much more simple than what we're seeing here. So this is all that we're going to do. And to get back, we're just going to take the transpose of the weight matrix. So we're going to see a lot of weight multiplied by, or weight transpose multiplied by weight in order to give us some weight space. So as we jump into it, what we're going to see is these are going to be our neurons, vertical and horizontal. These are our two neurons. And we're going to have 5 features. There's going to be 2 dials that we are going to play with as we go through this entire paper. There's going to be the sparsity dial and the importance dial. The sparsity dial just says as you turn up the sparsity, this is the probability of this feature showing up in the first place. So we have 0% sparsity to where every single time, every single feature is going to be present. And as you turn up the sparsity, what you're going to see is that each feature has a probability of just not showing up. To where as we increase in sparsity, the input, the features, are mostly just going to be 0, and only rarely do they actually show up. The other one's going to be importance. The importance is going to be a multiplier on the loss function. So it's going to range from 1, and it's going to go down close to 0. And so you're going to have some most important feature that the network really prioritizes, and it's going to go down to a least important feature. So what we're going to see here is superposition. So we have our toy model that we're learning on, and we're having a superposition. And the superposition is of features being crammed into neurons. This is the toy model of superposition. If you understand this image, you got the whole paper. You are totally set. So, as we see 0% sparsity, the network is literally just going to take the 2 most important features and say, well, these are the 2 that I can represent. These 2 neurons can represent those 2 things and nothing else. And so you're going to take those and just drop everything else to 0. You're just going to put those right at the origin, and they're just going to be gone. But as you start to increase sparsity, what happens is you're able to say, okay, so if both of the features show up inside of this dimension, that's not a good thing. That's a pretty bad thing, but they usually don't. So we're going to make the assumption that we're not going to see those features, and we are going to put them in. So one single neuron is going to represent 2 of these features. And so it's going to go into superposition, multiple features inside of the same neuron. And as you increase in sparsity, you actually go from having right angles, these used to be orthogonal, to almost right angles, to close to right angles, just because you want to cram as many features on the inside as possible. But the thing is, as you keep cramming more and more, what you gain is interference. This is going to be the crux. This is going to be the thing that limits how many features we can actually put into the network. So if you have this feature firing as well as this feature firing, what you're going to see is a linear combination that shows exactly in the same feature. The network is not going to be able to disambiguate as to are these 2 unfortunate features firing or is that singular feature firing. You have to make assumptions about the sparsity. And this is going to be the through line of the entire paper. What the neural network is actually doing is it's trying to increase the number of features that it can represent, because this increases its representational power and allows it to minimize the loss further. But this is going to be balanced by the interference that it actually gains because of this geometric interpretation of the superposition of the features inside of the neurons. The interference is going to cause you to start losing if you have too many features. So you want to maximize the number of features that you have while minimizing the interference that you're actually going to see. As we jump to the next slide, what's going on?
What's feature important? How do you know a feature is important?
It's literally just a scalar multiplied to the loss function. So in the case where they all have the same importance, you just have a regular loss function, x minus x prime. However, here you have some importance that's literally just going to be some linear scale going from 1, and it's going to start scaling down and down and down to just like 0.1 or something like that. So it's just going to affect the loss less, leading to slightly prettier pictures to where, as we jump to the next one, we see that we have a whole bunch of dots on the left, but none going to the right. That's because we're going to scale the importance of features that we plug in. We're going to have 20 features in 5 dimensions with an importance that is going to start scaling downwards. 0.7 times I, where I is the ith entry. And it makes it to where you can just see that it starts to flow left to right, and it's really pretty. And that's kind of one of the main reasons that we're going to have the importance feature. What's going on?
Could you go back a slide and maybe explain again? I didn't fully understand why 0% sparsity leads to dedicated orthogonal dimensions.
That's actually going to be 2 slides away. Would you mind if I jump straight to that real quick? But the reason for that is that, so you don't want that if you have if you have representation at all times. Because whenever you actually have all of the features always showing up, that interference is going to dominate. Let me actually jump back here. If you actually have all features at all times, the interference is going to completely dominate, and you're never going to be able to differentiate between which feature is actually going on. So if we had more than this, because as we start to decrease sparsity, as the features are always present, we actually start to become more like a linear model. And so as you always have them, it has to figure out a way to say, okay, so every single thing is present, but we have to figure out a way to map these weights, because we only have the 2 ways to actually figure this out.
So isn't that related also to the data? Because data is going to determine the presence of the model.
Exactly. One of the assumptions that we make is that we are going to have a very, very sparse language. That's just an assumption that we make throughout the paper, and so that way we can increase the sparsity in order to understand the superposition.
So, just to complete my chain of thought, if you're saying the more, if you have few number of features, you can have them more orthogonal or like further away from each other, but then your intelligence is also limited because you can represent fewer things.
That's exactly
And as you increase the number of features, you can represent more things, but now you run the risk of having interference with each other. So you're trying to come up with an optimal arrangement so that they don't interfere with each other.
That's exactly it, yes.
So interference here is not knowing which feature activated the neuron.
Exactly, yes. Yeah, so technically what the network is doing, at least they say this in the paper, is that this 2-dimensional network is pretending to be a 5-dimensional network that doesn't have superposition. However, because of the interference, it's a noisy simulation. So we are noisily simulating a network larger than itself that does not have superposition. If that helps clear it up at all. What's going on?
How does this model account for features that are well correlated versus features that are not correlated at all? For example, if you have 2 features that are well correlated, you might want to declare that they don't go on the same neuron, they go on antipolar locations or whatever.
That is
If you have
really
uncorrelated and anticorrelated features, that might account. You might want to represent them differently.
That's an amazing question. And unfortunately one that's just beyond what I'm going to be able to get to in this talk, but if you want spoilers for what I'm not going to be able to cover, the network knows this, and it wants to separate out things that are correlated, and it wants to put together things that are anti-correlated. Because if they're anti-correlated, you're much less likely to see them together, meaning that you're much less likely to have that interference. But if they're correlated, you want to separate them out to separate dimensions, to separate sets of neurons, because they have an increased chance of showing up together, and you can actually use more neurons in general to represent those correlations to have a finer resolution within the network. So it's going to create these subspaces of anti-correlated pairs. Let me jump down to it, because it's a really pretty picture. I won't be able to show it for too long. But you're going to have sets where these are going to be correlated, and you're going to have almost no superposition in these subspaces of your latent space. And as you jump over here, you have a lot of superposition. Although I can't do too much more than just show this image, just because it's a little bit beyond. I do apologize for that. Are there any more questions?
Can I actually add to that?
Yes.
Because I think that's a great question. There's also like a lot of similarity metrics that people use. So like basically like, to basically figure out if they want to fit it in that space or not, as well as like what neural network will also do. So that's like something that adds into some of this. But yeah, a lot of this stuff, the work that you were showing there was like things like some middle school, or they were doing some machine learning stuff like this. Like they were called like sub-vector machines. If anyone's familiar with those, but that's essentially kind of another way to kind of create those maps or those classes.
Could we talk after this? Because the correlation of features is actually what I'm in a small research project doing, and I've never heard of that before. That's really fascinating. For some reason, all of the features, in theory, based on this paper, it's not supposed to put those things together. You should expect that correlated features should not be put into the same neuron superposition sets, but it does. And I don't have a good reason why. Maybe somebody understands it, but I don't.
Yeah, I can take a look at it. Typically, like a really simple distance metric you can think of is like the Euclidean distance metric, right? Which is just like just draw a triangle and then it's like measuring distances between points and seeing if they're close enough or not close enough. Now,
around a lot of different kinds of distance metrics, but some perform better for some certain situations than other situations. So sometimes you can even take those certain distance metrics that can become more specific. So yeah, it's kind of fascinating. But yeah, we don't know yet.
Yeah, apropos that point, it seems to me your distance metric would be very dependent upon your loss function.
Yes, absolutely. And
Yeah,
this
that's true. Yeah, that's true. Yeah.
It's a mess. It really is. What's going on?
So I want to make sure I understood this paper. I think if you agree with what I'm about to say, I understood it. If not, I'm going to have to go reread it.
Absolutely.
So what they're essentially saying is it's superposition because each feature is not a single thing. It's really the combination within the vector.
I'd say each neuron can be triggered by different features.
Okay, got it.
It's
So,
superposition because multiple features can cause a neuron to fire.
okay, got it. So essentially we're saying a feature is what gets the neurons to fire.
Yeah, and
Okay.
I think I completely agree with what you're saying, because it sounds like you're saying that what makes a feature is not extremely clear.
Right.
And I totally agree. What makes a feature is not extremely clear.
Right.
Into the neuron, or it's just.
Yeah, it goes into a neuron, but the three definitions given in the paper are non-comprehensive and it's very a biased thing.
Gotcha.
And so that's the main question, because it seems to be that a feature is a thing inside of the network that starts to disambiguate the inputs and starts to understand its environment and split its environment into meaningful pieces that help it minimize the loss. But
So if you're wanting a feature, you pretty much have to look through the full activation map of the network.
yeah.
Okay, got it.
So-
So this is essentially a linear algebra span problem where you're trying to find maximum potential span of the network. So it's pretty much the same, like, okay, imagine you have one layer network for a minute. To represent a handful of K classes, you need at least 5 neurons to fire per each K class.
Yeah.
You would essentially then have a network that would then essentially be K over 5 classes, right? That's its potential. So as more neurons fire, you don't actually want that. Because if multiple neurons all want to activate for that feature, they kind of like collide with each other.
No, they meaningfully collide with each other, because you can
Okay.
also, the interference, this is spoilers for later, but interference isn't actually strictly a bad thing. It's a tool to start to minimize other things. You can use the interference as a tool in and of itself. Amazing questions, by the way, guys. Keep them going. What's going on?
I just want to comment on, so here we're talking about neurons and features interchangeably. This is interesting. I think, I'm not sure if they're going to this, but some of the other papers, they point out the multi-layer perceptron layers are sort of unique in that we do find these quote-unquote basis aligned features.
Yes.
Or if you look at individual coordinates in your MLP layer, they do correspond to different features. But this is not universal in like common architecture today. Even if you look at transformer models with different layers of transformer that aren't MLP layers, you don't find these quote-unquote basis aligned features. Anyway, that's sort of tangential. Just wanted to point that out.
Awesome.
Yeah, well, I was wondering like what the transformer model with a feature, I guess at least with like a row former kind of model, I was wondering if maybe a feature could be defined by superposition of fundamental frequencies of the attention layer. So you have like your attention block, it's essentially like a wave because of that row former architecture. I'm wondering if you could essentially define it like sort of like a superposition of this, think about the frequencies.
Kind of like a Fourier transform?
Yeah, essentially. I'm wondering if it's kind of built into that as that.
That's
And then I wonder if you could like, essentially like an inverse Fourier transform. I don't know, something like that. I don't know, I'm kind of like abstractly done.
No, I think that-
Yeah.
I think that's a really interesting idea, that would, I think, correct me if I'm wrong, kind of imply a non-locality, a universality across it. But this is actually kind of like doing a strictly local thing, where it starts to create these local manifolds in the geometry of the neuron space. I'm sorry, that was a shit shot. This basically just makes these like little parts of the network inside the latent space. And it takes that and then it chops that up, and it takes that small one and it chops it up, and it takes that small one and it chops it up. So I think the idea is really interesting, but everything I've read is strictly local.
Actually, I think there's onto something, because frequency, right? If you spectrally decompose a feature, you would see its eigenvalues, and that would tell you everything about the capacity of the network to represent it.
Right.
Yeah, it's a algebra, right? There's some sort of correlation there. Like maybe like an
Oh, definitely.
So,
That's awesome.
so that slide, so what is it going up, what's happening from left to right here?
Oh, this is the exact same thing that we just saw a second ago. Before we increased sparsity, and because we increased sparsity, we minimized the interference, so we could fit more features in because we have less interference. This is the exact same thing. We have more superposition because as we go left to right on the graphs, on these gradients, we are increasing the sparsity. So the features have less and less probability of showing up. And inside of them, we see it primarily on the left and growing to the right because the importance starts the highest over here and drops as we go over here. And what we're showing is the exact same thing. The sparsity is going to drop and drop and drop and drop. So this is going to be compared to a linear model. If we look with no sparsity, whenever the features are always present, it actually acts the exact same as a linear model. And so what we're going to see is that as the sparsity increases, then you get superposition. But why is that? I'm going to kind of fly through this. There's a couple other details that I don't think are so important. So at the top, we're going to see the loss function for the linear network. And on the bottom, what we're going to see is the loss function for a nonlinear network. Now, technically, this middle line is going to be the most important thing, but it's a toy model. We're going to make massive assumptions. We're just always going to put x of I is equal to 1, which is going to be correlated with the importance or the distance that we have from the origin in the slide that I just showed a couple slides ago. So we're going to take this bottom line, and essentially we have the same through lines where there's going to be feature benefit. You want maximum features as you're actually going through the network because this increases your representational power. But the more features you have, the more you're not going to have like non-orthogonal things. The more you're packing features into these neurons, so the interference is going to get in the way. You're not going to be able to disambiguate. So here's the interference term. The interference is, in the linear case, strictly a bad thing. Now you can see W sub j multiplied by the inner product of W sub I. And so that's going to be, if we jump above, the off-diagonal entries. The off-diagonal entries are going to be representations of superposition. And so, in the linear model, it's going to be squared. It doesn't matter if it was positive or negative, you square it, then it's going to be added to the loss. Superposition is strictly a bad thing in linear models. But whenever we jump into our nonlinear model, guys, we have a relative. We have a relative. So if you have this W sub j times W sub I, then if you multiply them together and they're negative, if you look above the slide, you see whenever we introduce superposition, the red means positive, the blue means negative. So we're going to introduce a lot of negative superposition. The weights are going to be maximally negative in order to represent more features inside of the network. It's doing that because if this is negative, Rayleigh sets it to 0. And then you square it, 0 squared is going to be 0. Suddenly this term is now simply 0. The I is the importance from before, it's strictly a number from 0 to 1. And so you get this for free. In nonlinear networks, if you can assume a lot of sparsity, meaning that you don't have too much interference, a negative interference is going to be free in the loss function. So of course the network is going to go out and grab it. It's going to take hold of this thing and it's going to use it. So we should really expect to see this in the wild, and we actually do end up seeing this in the wild. Superposition has been shown quite strongly. We're going to take kind of a 90-degree turn, and we're going to talk about phase diagrams. Do you guys remember those from schools where you had pressure and temperature, and you had water, and you have solid, liquid, and gas? This is going to be something kind of similar, but instead we're just changing those two dials that we had before. It's going to be our feature density, which is going to be our sparseness, and there's also going to be the feature importance, which is just going to be the multiplier and the loss function, the I that we just saw on the last screen. So as you have density to where it's always here, we're going to have a much simpler model than we had even before. We have two features and one neuron. So at the very top, whenever both of them are always present, the neuron just has to choose. Which one am I going to represent? Am I going to take this one or this one? And the reason it's going to decide is based on importance. The one that matters to the loss the most is the one that it takes, because we want to minimize loss. Always, always, always minimize loss. However, as we introduce sparsity and we get to about 0.1, what the network does is says, I can fit them both. And it begins to do that. It begins to stuff them both into the network, and we actually get superposition. The important thing here is to see kind of the similarity between solid, liquid, and gas, and then only representing one feature, the other feature, and then a superposition of the two features. We're going to jump down into something that's showing something really, really similar. This is going to be essentially the same thing, but blown up and shown in a graph. So for the numerator, we're going to have have the number of dimensions, and at the denominator, it's the number of features represented within the network. As we go left to right, we're seeing different training runs as we increase sparsity. So as we start to increase sparsity, meaning the features are almost never present, we go into a deep layer of superposition. The numerator is not going to change. The neurons are the neurons. But the number of features represented is going to grow and grow and grow as the sparseness increases. Because as we grow sparseness, we're going to decrease the amount of interference that we have. So we see that it's going to start going down. But it doesn't uniformly go down. It seems to be sticky. It seems to be sticky at 1, and it seems to be sticky at 1/2. Why is that? It's because of the phase change. The phase change is the reason. So as we go down, this is going to be a lot, and it's really pretty. Guys, this paper has really pretty figures. So each line, each colored line, is going to be a different phase, exactly like we saw just 2 slides ago, solid, liquid, and gas. But this is going to be slightly different. I want you to think of these phases like we have a proton. This is going to be a little bit different because this is going to be strictly in 3 dimensions. This one is not limited to dimensionality. And we're going to take an electron and we're going to drop it on. Here, our proton is going to be our neuron, and our electrons are going to be our features. So we drop one down, and then it's just 1 to 1, as you see. 1 neuron on top, 1 feature on bottom. And as you add another electron, you're going to see that they're going to separate massively because of their electrical charge. The features are going to separate as much as possible because this minimizes interference. And then as you add another one on, it goes from the dipole into a triangle. And as you add another one on, it goes from a triangle to a tetrahedron. And you can add more and more and more, and the angles between them are going to get tighter and tighter and tighter, and you're going to go into this analogy for deeper and deeper superposition. You can see in gray, back here, the actual line that we just saw a second ago, and you're going to see these vertical stripes. These vertical stripes are training runs, and inside of the vertical stripe, you're going to see a bunch of dots. Each dot is a feature. The higher up the feature is, the more of a number, or the lower number of neurons it's going to have, if that makes sense. Where 1 to 1 is above, where the feature gets its own neuron. It gets a whole neuron all to itself. As you increase in superposition, what it's going to do is it's going to drop down to 3, 4, where you're going to have 3 different neurons and 4 features inside of it. It's a new crystalline structure. And then you go down a little bit more, you get closer to 0, and you get 2 out of 3. So it's going to be 2 neurons with 3 features packed inside of them, and then 1/2, 2/5, and 3/8. What's happening is that there are these submanifolds. As you can see up top, these are going to be different representations of training runs. Inside of the geometry, instantiated by the neuron space, there's going to be these sub-shapes made of features. These sub-shapes of features are going to have their own crystalline structure based on how they actually want to assemble in a quantized way based on the changing of the phase. The phase is going to increase. You're going to have more features per neuron in general for more superposition, but this is the main takeaway that I want you to have. There's going to be, inside of a neural network, more features than you have neurons, and the way that the neural network is actually going to assemble these things is it's going to create these submanifolds inside of the geometry of the neurons in order to actually figure out how do we collect and assemble these things in a meaningful way. And in fact, we've already seen this. This was exactly what we saw before. So where here you have 1 to 1, and this is the lowest amount of superposition that you can have. 1 feature, 1 neuron. As you jump to the side, you have the 1/2 that we saw before, because we're limited by geometry. We can't find a different shape. So you have 2 features packed into 1 dimension twice. And then you jump over and you see the pentagon, to where in 2 dimensions, you're going to have 5 features. So this is following exactly this thing right here. And this is the main takeaway that I hope you can have, to where the network is going to be balancing how many features it can have with the interference, and it's going to take a geometrical set and apply that inside of the neuron space. This is about where I planned on ending.
We have time for questions if anyone had any. Yes.
Does this imply that if you have too many features that you're showing for a neuron, none of the features are truly learned?
What do you mean by not learning?
So, as you said, like, in your first case, when you have like 1 feature for 1 neuron, it has a dedicated neuron to it, right?
Yes.
But as the number of features increase that are helping activate the neuron or not, each feature contributes like X amount to the activation of the neuron. Right? So does that mean that if you have too many features and too little neurons, none of the features are truly
always wants more features than it can have because that can increase the representational power. If it realizes that it has too many features, then I don't know if you can do that just because like it always does want more features. It's going to be balanced out by the word that I'm totally forgetting, the interference.
So there's also a question with toy example, right? If we have just 5 features, and you say the various parts, so it's how many points of data do you have? No, because if you say, sometimes it doesn't even show up. I mean, does it mean that in a sample you may have no feature showing up at all? Or you're always having at least one feature showing? What? I mean, is that just a negative sample?
That's a great
How does that
question.
relate? How many features, like, what's the ratio of like points on the sample versus the number of features?
No, I think that's a great point, and I'm going to be bold and make a guess, but I actually don't know the answer to that question. It makes sense to me that you have to have a minimum of one feature going off at all times, and as you increase the sparseness and have really good superposition, chances are you're going to get pretty much zeros across the board. However, only 1 or maybe 2 features are actually going to be present.
Yeah, but if you think of sparse or shallow networks, right? And if you the biggest issue with ImageNet used to be is very shallow networks and lots of data representations and a vast amount of features really that the points represented. And the network was unable to learn those because there's in theory too many features that it's trying to learn with too few neurons, which is what prompted my question. So is there like a sweet spot where having enough features and you're like where like if you go above a ratio between features and neuron where learning is hindered completely. Like there's too many features in the data, too few neurons.
That would be get to like interference, right?
Yeah, that would increase the
You would
interference.
just regulate for interference reasons.
Yeah, it's going to be primarily an optimization between features, but as you increase features, you increase interference. If you have too many features, you're going to increase the interference towards that, which is going to raise the loss, and always will not lower loss. So it's going to cause the features to start to bundle together. And like droplets of oil, they're going to start to group, or at least I find a great analogy of droplets of oil to features. Oh, another question.
With the phase change diagram, is that actually symmetrical? And if so, is that just a function of the features wanting to be as far away from each other as possible?
So the reason that it was symmetrical here is because we are setting all of the features to have variable importance, and we're going to pretty much scale all of the sparseness of all of the features, and we're going to very, very carefully measure the importance of those features. In the real world, this will not be true whatsoever, and we're not going to get this clean geometry is almost strictly because all of these are going to have the same importance, and they're all going to have the same sparsity as we continue one training suite. So in the real world, we're not going to get these very clean, beautiful shapes.
Yeah, so I think that this paper actually relates really well to the superweights idea, which is the notion that within these deep neural networks like LLMs, if you actually open up the weight matrix, most of these weights are near 0, and very few weights are like massive. What they found is if you remove any of the superweights, the whole network is dead. And therefore, so this kind of idea is like you have some cornerstone neurons that have to activate for concepts. And those are the superweights in the paper, and everything else is like, you can just move them around a little bit, but to some extent, it's like a network can define its sets of activation throughout its weight matrices, and that's what seems to represent the feature, right? Because it's in the superposition.
Yeah, so...
And on top of that, if you were to then just have, and I think this is what Sanat was referring to, if you have one vector, then the features are additive, right? Because you have to then figure which one of these in the layer you activate. Yes. But if you have 2 layers now, they become multiplicative because you have one layer and another, and so essentially I think that going back to what someone else said about symmetry, is that all these networks have these non-linearities that essentially let them jump to different spaces. And that's kind of how they create the superposition of many layers. So it seems like that's kind of how LLMs, because there's multiple research that keeps on showing the same pattern of LLMs develop this massive amount of sparsity. Now, as they keep training it, there's some reduction in the sparsity, but not a whole lot. And it seems that there's more of principal magnitude of activation becomes much more important for a handful of features. And that's essentially how a lot of very successful quantization schemes work, is they figure you have some very massive activations that you need to preserve, and the rest are like, yeah, they don't really matter.
That's really interesting. Everything that I've seen is that the feature space is completely decorrelated from the neuron space. And in fact, these features are going to be completely invisible if you look at neuron activations. You're not going to see them except with very specialized tools. So maybe there's something to that, but I'm just not familiar. That's really interesting.
But how can they be decorrelated in a way? Because I somewhat I see what you're saying, right? We can't look at a feature as we've called it and just say, try to predict the neuron itself. I would agree with that. But it does seem that there has to be some linkage within the neurons to create the feature, though.
Yeah, but the feature is going to be well distributed across the entire
Right, sure, I agree with that there. I'm just saying that you'd have to have some amount of co-activation to have a feature in the first place. And what it seems to be saying is that the bigger the transformer gets, there are very few neurons that are like the pivotal neurons, and then most of them don't actually matter. So it's saying that there's a handful of neurons that make this big connection, and the rest can just be proved out of the network.
So the interesting point, though, you can see like a lot of the more recent, very small LLMs that have been trained on a lot of tokens have far less sparsity than some of the big ones because the weights just are a lot more saturated, a lot higher entropy. And so you can kind of imagine like that diagram where there's the 5 features there. If you had a smaller network, right, imagine not just two-dimension, 2 neurons, only 1. Trying to represent 5 features on 1 neuron is almost impossible.
Yeah.
And so I think like as you add features to the network, the concept of superweights starts to go away because you're going to need to saturate as many neural dimensions as you possibly can in order to keep them roughly orthogonal.
Yeah, and that has been a theory proposed as well.
Right, and we see like integer quantization works far worse on smaller networks that are trained along.
Yeah.
I'm also wondering with this, sort of when we talk about the features versus activation, with an attention layer, you have the actual activation, which seems like it's sort of supercharged, related, but the actual embedding, self-attention, the embedding, the matrix that makes that up. I guess I'm just wondering if maybe that's the actual embedding matrix is more akin to the features than the actual final activation.
That's a really interesting question. So right now, the current belief is that the most important part of a transformer or any network is actually going to be the residual stream, the residual connection famous from, of course, Reston. And so the idea is that there's going to be this additive space where every single attention layer and every single MLP layer is actually just picking and pulling from very specific parts of this residual stream, this fire hydrant that's blowing through the entirety of the network. And so it takes that and it takes very specific things and it rearranges them. It takes them and it distributes that information to the more important places that it might be important for following layers.
It's like a moving particle through each layer.
Exactly, yeah. To where this is going to be the source for the vast majority, well, this is the home for information. And then we take that and we augment it in such a way that it's prepared to be an output. And
the features are like the velocity in each direction of the particle.
Features in this case would
The different
be a lot like that. Yeah,
You could think of it as like the activation magnitude per neuron, or which one's activated together. Because I think this is the thing, the paper doesn't distinguish between, and I don't know if it does it distinguish between magnitude of activation of per neuron?
Not at this point.
Or does it just say which one's just activated, means 1 or 0?
Magnitude is an incredibly important piece, but in this paper it's strictly a direction. Magnitude and direction are taken into account in future papers, but this one, no magnitude.
It makes sense here.
Yeah.
Alright, everyone give them a round of applause. So since we have a smaller turnout today, we'll go to 8:50, so you can mingle here till 8:50. After 8:50, you've just had out of the up so that you get a nice little email whenever we do these every month.
Woo! All right. We're so smart now, we're gonna download DeepSeek, and we're gonna make DeepSeek for you.
Doesn't matter. It's literally just the space where we're used to living. Like more and more, as I mentioned, I used to think that, oh,